Welcome back, everybody. Thanks for checking back in. We're going to be continuing with our Chapter 6 notes today. And we've talked about Newton's three laws. Well, it's third law, but as part of all of his three laws. His first law dealt with inertia, that is, objects at rest stay at rest, objects in motion stay at motion. The second law was a very, very famous one. That is that force equals mass times acceleration. And the third law is what we call the action-reaction law. That is, for any action pushing this way, there is an equal reaction or an equal force pushed in the opposite direction. What we're going to continue with right now is very parallel to Newton's second law. That is, force equals mass times acceleration. And that brings us to the concept of weight. Oftentimes, people get weight and mass mixed up because sometimes we weigh things in kilograms. Or we say we measure the mass of something in kilograms. Other times we measure in pounds. But the problem there is that not only are they two different systems, kilogram is the metric system, pounds is the English system, but pounds isn't even a measure of mass at all. It's of force. Think about it this way: your weight. You're a person right here, and you're standing. You're about ready to stand on your bathroom scale, okay? You know your body has mass. That's what gives you a body. It's made of matter, therefore it has mass. But you step onto this bathroom scale right here, okay? It's measuring your weight. Now, it's not really telling you about how much matter is in your body. What it's telling you is how much force your body applies to that bathroom scale, when you step on it. It's really a force meter, honestly. Pounds is an English unit for force, just like Newton's is a metric system measurement for force. So it would make just as much sense for you to step on a bathroom scale and it register your weight in newtons, because weight is really a force. It's not a measure of your mass at all. So sometimes we'll abbreviate weight with a W right here. The problem with doing that is that when we get into when we get into work and kinetic energy and potential energy, work is capital W, and so that'll mess us up. So we're not going to call it W, although you can do that for the time being. We're going to denote the weight force as F sub G. This right here, this force, you can say force due to gravity. The force that gravity creates, because Newton's second law tells us that since a force is created by a mass undergoing an acceleration, if you have some mass, subject to the Earth's gravity, which we know to be an acceleration, that's 9.81 meters per second squared. If we take a mass and accelerate it at that rate, it will produce a force, and we call that force the weight. We call it the weight. Why, you ask, did I not put a negative in front of this? Well, because whenever we have G, it's simply the absolute value of the acceleration of gravity. We're not worrying about the direction right now. Usually your force is directed in a downwards direction, so it's just assumed that it's going along with the same direction as gravity. And in pretty much all the cases we're going to use it in, that force that is caused by gravity is going to be directed downwards, which is why it tells us this right here. It's always in the same direction as G, which in our case is going to be in the negative Y direction. But this is really important. This is going to be for any object that we deal with that undergoes forces. As long as it's on Earth, it's going to be experiencing a force caused by gravity, among other forces as well. So let me just do a quick little example right here. I'm just sort of making this up. I'll change colors here to like a dark blue. So say we have an apple. Okay, maybe I should make that red. We have an apple right here. I don't know what kind of apple that is. Let's try it again. Has that little thing on the bottom. Now, most apples I'm used to have the little bite thing taken out of them, but there we go. We have an apple right there, and it's sitting on a bathroom scale. All right, now this apple has a mass of, oh gosh, I'm going to be a bad judge of this, 0.5 kilograms. Oops, KL, kg, right? 0.5 kilograms. All right, and so the question is, what is the force? What is the force of gravity that is created by this apple? Okay, well, we take the mass of that apple, 0.5 kilograms, and we multiply it by the acceleration of gravity. We know that to be 9.81 meters per second squared. And of course, since I made this up, I don't have this actually done. 0.5 times 9.81. I get, that's a familiar number, 4.905. 4.905. In fact, you know what? I'm not even going to do that. I'm going to just say 4.91 newtons. Okay, so the mass is half of a kilogram. That is, the amount of matter that it contains is 0.5 kilograms. But due to Earth's gravity, it is creating a force of 4.91 kilograms. I'm sorry, 4.91 newtons downwards on this scale right here. This scale being designed to measure force, therefore reads, oh, okay, that's 4.91 newtons, our scale says. And so that gives us a sense of how much matter is in that apple. But weight is really simply a force. When you step on a scale, it's not measuring your mass, it's really a force meter measuring the force that your body, under the acceleration of Earth's gravity, is creating on that scale.